So today we're going to talk about correlations. Correlations are a measure of the relationship between two continuous variables. So you know that if for whatever reason you don't believe that you don't have two continuous variables, correlations is not the correct test. That said, we're going to be using the packages ggplot2 and coreplot. If you don't have them installed, you can, with this syntax that will be uploaded to the course website, you can uncomment this and install your packages. So the data that we're going to be using is a dataset called mtcars. It is preloaded into R. Therefore, you do not need to upload that data. Let's take a quick look about what data is available in mtcars. With this question mark mtcars, we get to see a little bit as to what this data is. So data extracted from the 1974 Motor Trend US magazine. There's 32 observations, and we will have variables miles per gallon, number of cylinders, the size of the engine, which is displacement, gross horsepower, rear axle ratio, weight in thousands of pounds, quarter mile time, VS, which I believe is whether it is the engine is in V or is it a straight, depending on the number of cylinders, a straight 4, a straight 6. Transmission, it says AM, 0 for automatic, 1 for manual. Gear, number of forward gears. Carb, number of carburetors. Obviously, this is somewhat of an old data set, given that I believe most vehicles have, if not all sold today, have our fuel injection. So let's take a quick glimpse of the data with the summary. So here we have miles per gallon. It goes from 10 miles per gallon to 33.9. Cylinders, we have 4 through 8. Displacement, we have 71 cubic inches all the way to 472 cubic inches. We have 52 horsepower to 335. We have DRAT 2.76 to 4.9. Weight is 1.5 times 1,000, so 1,500 pounds, all the way up to 5,400 pounds. The quarter second, between 14 and a half seconds and 22.9, and so forth, so forth, so forth. That said, let's dive into this. Obviously, with new data, you should do some more exploratory data analysis using univariate statistics that was covered in previous classes. So let's graph the correlation and see what exactly it is that we're testing. So when we create a correlation, basically what we're doing is we have a bunch of plots. We have a bunch of observations, and between these two x and y, meaning two continuous variables, in this case miles per gallon and horsepower, and correlations try to fit a line. So the correlation algorithm is going to fit a line in a linear Pearson correlation when what we're testing is the slope of this line. Is it or is it not 0? So the null hypothesis is that beta, the slope of this line, is 0. The alternative is that it is not 0. We'll go back to this graph in a moment. So without further ado, let's do our first correlation between miles per gallon and horsepower. Here is all the syntax that you need. Core test is the function. We're using mtcars, the variable miles per gallon, versus mtcars dataset variable horsepower. So as we run this correlation, we have a few values. We have the number of the degrees of freedom. We have a t-value. We have a p-value. Given that this data has 32 observations, I'm going to choose my alpha as 0.05. Alpha being the bar, where we decide as far as we compare the alpha to the p-value or the p-value to our alpha. If the p-value is below alpha, then we reject the null hypothesis. If it is above, if this p-value is above alpha, then we retain the null hypothesis. In this case, it's 1.7 times 10 to the minus 7. This is a very small number. It is 0. Then 6 zeros, and then 1788. We have a correlation that we are 95% confident. This has to do with alpha being 0.05, which is a default. And we're 95% confident that the correlation, or rather that beta, the slope, is between 0.88, negative 0.88, and negative 0.58. Our estimate for beta, or the correlation, is negative 0.77. So we have rejected the null hypothesis, so we would write the relationship between miles per gallon and horsepower is significant. Two more things that we need to say. We're going to talk about the size of the correlation. I have decided that 0.77, or the absolute value of this correlation, 0.77, is large. So I'm going to say the correlation is strong, or rather, I can say that it is large, and it is negative. Now, for that email that you will be sending to someone that is not well versed in statistics, you will say that the more horsepower, the less miles per gallon. That's the simplest explanation. Here we have another correlation, which is between miles per gallon and the size of the engine. Again, we see a p-value that is very small, and it is negative. So the p-value is below our alpha, so the relationship between miles per gallon and displacement is significant. The correlation is strong or large, I believe so, at 0.84. And it is negative. I see the negative sign. The more displacement, the less miles per gallon. Or we can say the bigger the engine, the less miles per gallon. Now, we can do this over and over and check all our correlations, but we can run all our correlations all at once, although it will not give us p-values, but it will give us the betas, the estimates, with this code. And I've inserted it into this object called core matrix. I can just print this out by running this. And as you see, what we have is a correlation of all the variables with all the variables. When you see a 1.0 is obviously the correlation between miles per gallon and miles per gallon, which is a perfect correlation. This is a way where we can see all our estimates. We don't know which ones are necessarily significant or not, but we can take a quick glimpse of all these numbers. Another easier way to take a quick glimpse is that using this saved matrix, I can run this core plot. There are other correlograms that can be created with other packages. They all do the same thing. It's really a matter of preference. Neither is going to be really better. But in this way, I can see that where I have a dark red, it's a very negative. And where it's a dark blue, it's very positive. And these lighter shades are a weaker correlation and maybe even not significant. So we've already obviously seen very strong correlations with our first two examples. Now I'm going to take a look at horsepower and gear. It's a very light color and has a small circle. So it seems like the amount of horsepower and the number of gears a vehicle has doesn't seem to have a very strong relationship. It is on the reddish side, so it's slightly negative, I guess. But let's test this out. So this is the whole idea for creating this, is that we can actually try to find either very strong relationships or very weak relationships. So if I test out horsepower and gear, I run this, and I find that the p-value is 0.49. it is way above 0.05, my alpha. That said, I don't care about anything else after here. I don't care if it's negative or whatever. My p-value says that I am going to retain the null hypothesis and that beta is equal to 0. Therefore, the relationship between horsepower and gear, or the number of gears, is not significant. In layman terms, the amount of horsepower and the number of gears have nothing to do with each other. One last little thing is that if you have a data set that has, let's just say, many observations and you want to change your alpha, okay, we call this correlation over here, where we have 95% confidence intervals, which again is your indication that the alpha is set to 0.05. We can change this to 0.01 or anything we want. So all I have to do is confidence level. I'm going to change to my alpha to 0.01. And let's run this. Now what do we see? We see that the p-value before was 938. Here's the same p-value. The p-values are not going to change. Okay? Your t-statistic is not going to change. Degrees of freedom are not going to change. Your estimate is not going to change. The only thing that's going to change are your confidence intervals. The stricter the test, the wider the interval is going to be. This is between negative 9.2 and negative 0.7. Now this is between negative 938 and negative 0.64. It's a wider interval. And again, when this interval contains the number 0, that is when your p-value, okay, will become, not will become, but will be smaller, will be larger than your alpha. So that said, let me just put a little comment here. With alpha equal to 0.01, and let's make that comment over here. Default value. Okay, let's go back to one last thing. Let's take a look at this graph. When we plot this graph, if you notice, we have our correlation line right over here, and we have this gray area. This gray area is the 95% confidence interval. If you're wondering why it's a little bit wider in some areas and tighter in others, it's all about the number of observations that is making up this little estimate. Okay? And if you wonder also where this line came about, this line is a line that best fits these observations, meaning it minimizes the sum of all these distances between the observation and the correlation line. And that's about it for correlations.